My name is Isha, and I work with the Horizons Achievers program team. And I'm very excited to be moderating this webinar today because we're going to be focusing on the biosciences course that we're offering in addition to this summer. It's the cosmic dance of your immune system. And I think it's the most poetic title that we have for any of the courses that we're doing this summer. And I think that's very fitting as well because immunity does end up being quite poetic in a lot of ways. I know we try to look at sciences as cold, hard sciences that are separated from the arts, but many of them have actually shown that there is a great overlap, and I think they work very well in an interdisciplinary fashion. I'm pretty sure a lot of us have been following the Artemis 2 journey, and it's been similar where we've been able to see the highlights of humanity and sciences coming together. So, in similar ways, which is what we experienced in COVID 19, the concept of herd immunity is what we plan to cover today. Without giving away too much, I'm going to start with the sharing my screen and actually starting the webinar. One moment. So essentially, we're here today to do the learning circles titled as Immunity in Numbers, very well fitting for herd immunity being explored today. And we're going to be getting input from Nihar, who's actually the teaching fellow for the cosmic dance of your immune system. And I'm very excited to see how he brings in his wealth of experience to actually give us a glimpse into the classroom today. Thank you so much for taking out the time to join us, Nihar. With this, I'm going to pass the mic over to you so that you can actually take over. And please let me know whenever you want to start sharing your screen instead.
Yeah, thank you so much for the Arisha. I will just take over the sharing right now, if that's possible. Just
Okay,
one
let
second.
me just stop sharing my screen and you can actually take it over. Yeah.
Yeah, while I'm doing that, do any of you want to talk about what herd immunity seems to be for you? I know it's a very common topic, and a lot of people here might already know what it means. But if you could drop whatever you think it does mean in the chat box, it would be great while I'm just sharing my screen. It'll also make me feel like you're actually listening to me, so that would be great. Yeah. All right. I hope this is visible or will become visible. Yeah. Thank you so much. Okay. Now, I don't know if I will see people text in the chat, but all right. Um, Let me just start anyway. So, herd immunity is a very, very fundamental principle in immunology. It works on the principle that if there are enough people which are immune to a certain virus, then the spread of the virus is limited. And by doing this, we can actually stop the virus from spreading to anyone. And this leads to the virus eventually being defeated from the population. Now, this is something as a bioengineering principle is something that has helped humanity a lot, especially in combating things like smallpox. Smallpox was one of the first viral diseases which was actually eradicated from humanity. Though I think there were some recent news articles I saw about some kind of resurgence, but let's not get into that right now. The principles of this is very basic, very understandable, which can be seen in this image that I have on the left. If most of the people in a population are immunized, if the virus cannot infect them, then the virus will not find enough number of suitable hosts. And thus, this will lead to the end of the life cycle of the virus. If the virus does not spread, the virus is defeated, no more virus, and no more sick people. Now, this is obviously something that all of us must be familiar with since we have just come out of a pandemic, of a global pandemic. So, herd immunity is not, I'm sure, an unfamiliar concept to everyone. So, let's take it a little further. Now, why is it that herd immunity is so important, not just for you, but the people around you? So there are certain segments of the population which, due to different reasons, such as being immunocompromised to different disorders, for example, HIV, or having undergoing cancer treatment, or just being under 6 months old, this segment of the population is actually not be able to take vaccines themselves. So they are a segment of the population which is really at risk for viral infections. Why taking vaccines by making sure that the majority of the population is actually immunized. You're not just protecting yourself, but also the people around you from taking the virus. Now, this has been taken in a lot of different cases. I won't go into a lot of detail right now, but a lot of studies have shown that how immunizing the majority of the population, say 70 to 75, 70 to 95%, actually leads to reduction in viral spread, even in the segment of the population which is not vaccinated. So here, for example, you can see that there are some segments of the population which cannot take vaccines. For example, really young children, people who are immunocompromised due to chemotherapy or due to being infected with another disorder. We protect not just ourselves, but the people around us by taking the vaccines. Now, I love talking about biology. I love learning about biology. I love sitting in a classroom and learning. But the best way to learn, and this is something that is true across disciplines, is to interact, right? And just for that, I've also found this link that I'm hoping that one of the other panelists can share with the rest of the attendees in the chat. But if you go to this link, you will find some very basic definitions about herd immunity. And another thing you will find is a very good simulator. Now, what I'm going to do is I'm going to stop sharing right now and open this website and share that as well. And we're going to go through this simulation together. So if you'd like to follow along, please definitely do so. Let me just open this. Very quick perception check. Is everybody so far understanding what all I've talked about? If I could get some thumbs up in chats or plus ones, either would work. While I just open this up. Please also feel free to, yeah, you raised your hand. Is that a question or is that supposed to be a thumbs up?
That's my thumbs up.
Right. I thought so. But if any of the attendees have any questions, please don't hesitate to unmute or just raise your hand or just start talking, and I will definitely attend to your questions as well. Let me start sharing this simulation. Right. Now, one of the things that people really are confused about is how much of the population needs to be immune to a certain disease before it can be eradicated, right? Now, that depends on a lot of factors, specifically things like how infectious this viral virus is. For example, is it really easy for it to infect other hosts? Is it really hard for it to infect other hosts? Can our natural immune systems combat it easily or not? A lot of factors come in, making some really complicated equations that we're not going to get into. But basically, what we're going to do with the simulator is we're going to see at different immunization rate what actually happens. So now, as we all must know, there are two ways to be immune to a certain virus. One is to be infected by it, in which case your immune system produces a lot of B cells and T cells, which then remember the virus. And because of that memory, whenever the virus is approaching your body again, your immune system can react faster and more efficiently to eliminate it. The second way, of course, is through vaccines. Through vaccines, what they do is they inject a small amount of either inactivated or very weak form of the pathogen, which allows your immune system again to understand what it looks like, what they need to look out for, and gives them the memory that they need to be on to know that when this pathogen comes again, how to recognize it and how to act against it, right? So first, we're going to go with a 0% immunization rate. I hope this is visible to everyone, but I will zoom in a little more. And we're going to see how long it takes for everyone to be to be immune and for the virus to be completely wiped out. So we'll characterize that by seeing no red spots at all. Here you can see that no one in the population is vaccinated. So all they can do to have any kind of immunity against the virus is to get infected by it. The green circles here showing you people who've recovered from the disease. Now, of course, while this is a way to combat viruses, this obviously will come with a lot of danger, right? Because a lot of people may not recover from the virus, and this leaves them susceptible to further decrease as well as fatalities, right? Okay, it seems we have completely eradicated the virus now. Now let's see how different rates of immunization actually fasten this process. So we'll start with 25. Yeah, you're seeing some blues here, which means there are some vaccinated individuals. Very nice to see. This is probably what the earlier days of COVID looked like when people had just started taking vaccines. Let me just, yeah, okay. So here, while the spread of virus that you'll see is still quite fast, you will see that it is interacting with a lot of these blobs as well, which are people who are already vaccinated. And since it's not able to infect them, the spread of the virus is a lot slower. But still, obviously, from the red spots, you can see that there's still a lot of infectious spread happening. Okay, I think we're almost done with all infections. Since the link has been shared, I really hope you guys would be able to follow along and look at how different vaccination immunization rates actually lead to different time taken for the virus to be fully eradicated. Okay, looks like we're done with 25. Now let's skip 50 and jump straight to 75. Now here we see that a majority of the population is vaccinated, and you can see that our infected individual is actually having a hard time finding people to infect, right? This is all, of course, the simulation is based on very random chance of the individuals, infected individuals, interacting with either susceptible or vaccinated people. So in real world situations, this number can change a little bit, the time taken and the population required for a virus to be stamped out. Okay, this was actually pretty quick. Let me just restart. Let's do this again. I think our virus was just incredibly unlucky, and it was not able to infect a lot of people at all. I think here as well, it's gone off screen and now we can't see it. Okay, so let's skip straight to 95%, where a huge chunk of the population is vaccinated, and we can assume that the only people not vaccinated are people who are not able to take vaccines right now. Yeah. So very easily you can understand what herd immunity is doing here. By having a huge amount of people who are vaccinated against a virus, it's unable to spread. Just by sheer chance, it's not able to encounter people who are susceptible. And even if it does, let's say we restart this again and it's able to meet one of the yellow particles, it's not able to spread further at all. This is why vaccination is such an important bioengineering technique to have, and why so many policies and so much social and political attention has been given to it in the recent times. Let's do one more for good measure. Oh, very luckily, it was able to infect a second individual. Yeah. All right, great. Since the link is shared with you guys, I'm assuming you will be able to run your own simulations as well. There are some more advanced ones that are also available online, and if you would like to find them, you can definitely reach out to me and I will share some of them with you. They delve into a lot more of the equations and mathematical formula that comes behind tracking infectious disorders. So instead of going over that right now, where it would become increasingly more complicated, I will leave that for your self-study as well. I wanted to do this kind of simulation just to give you guys a little bit of an idea of what it will look like in the course as well. Because at Ashoka, we really emphasize application-based learning and we really emphasize interactive learning. So I wanted to give you guys a chance to feel what it might feel like to be in the classroom at Ashoka for 15, 20 minutes. But yeah, this was all I had so far. I'll hand it over to Isha again, and she can take over. Isha, would you like me to stop sharing?
No, actually, if it's okay with you, can we go back to the activity? Because we had a couple of attendees that joined us later, and I actually had a couple of questions to throw your way, which I'm worried may
Okay.
be a bit advanced, but I think I'm just curious because we went through COVID-19 recently, and there was so much talk about herd immunity in different ways. So if you could touch upon that. So, one thing that I did want to ask that the simulator is based upon people getting vaccinations, right? And I
Yeah.
remember the talk during COVID-19 while we were developing the vaccinations and they weren't in place was the concept of herd immunity coming into play, even if people were infected and had recovered, and then thus the population would have immunity against the virus. Could you touch upon that a little bit?
So definitely, like I was mentioning earlier, the natural way of acquiring immunity is to be infected by the virus, right? But the reason why we want vaccinations to take place on natural infections is because natural infections, of course, are a lot more dangerous for each individual. And depending on the individual's own immune system and their own health, it may lead to either further complications or even fatalities in some cases. Vaccinations introduce the immune system to a very weak, if not fully inactivated form of the viral particle. Sometimes it's not even the virus itself, but a small protein of the virus. And what that does is that it creates a very safe environment for our immune system to learn about how to recognize the virus and how to prepare for it. Now, this means that vaccinations are incredibly safe and a great way for our immune system to learn what this pathogen looks like and to get immunized against it. I hope that clears it up a little bit. While natural immunity is something that can be acquired, it is very dangerous for us to let the entire population get infected and then acquire immunization through that.
That actually really does answer my question and has me connecting some of the dots. I remember that in some cases during COVID, there was also moves that, oh, we should move away from having the masks because we can just get herd immunity if all of us are infected and we can recover.
Correct. Yeah.
But I think that did come at the danger of immunocompromised people being susceptible to the virus and being susceptible to the complications, as you mentioned, whereas the vaccine was a much safer way. I still know that there are many immunocompromised people who can't take the vaccine, right? So, in some ways, it's not just for ourselves that we need the vaccination, but for the community as a whole. And that kind of makes it safer for us to not have to wear masks for the spread of COVID-19 anymore. Now we do wear masks, but that's because of pollution, and that's a different story altogether. And unfortunately, there are no vaccines against pollution other than
Yeah,
just
very,
making the
very unfortunate.
environment.
As someone who has dust and smoke allergies, it's very unfortunate that there are no vaccines against pollution.
Yeah, I think that would be really helpful. Like if evolution could have just helped us to be safe against these, but I think that's just not possible at all. I was also curious about some of the things that I saw in the simulation, right? Where when an infected individual came across someone who was susceptible, they infected them as well. But then after a certain period, they'd recovered. So then the vaccinated people would keep on increasing in number, and susceptible people were reducing in number as well. So could you touch upon a little bit about how, even if we have some people who are infected with the virus, but we have a larger chunk of vaccinated individuals or populations, that does help in curbing the spread, and what's the rationale behind that?
Yeah, definitely. So let's forget about the complicated concepts like how a virus is infecting your immune system. Let's forget about infection rates. Let's forget about the virus at all. Let's look at pure chance. Now, let's say there's a random probability that one of our infected individuals here in red will encounter either a vaccinated person or a susceptible person. Just by having more amounts of vaccinated individuals, the chances that the infected individual will encounter a vaccinated individual is higher, right? Just by numbers, correct? Now, because of that, the virus's lifespan does not have enough time to actually find and infect a susceptible host. Because of that, the virus itself will die out and it will not have the time to actually find and get another host so that it can keep spreading on to multiple people. So forget all concepts of immunology, forget concepts of how viruses are made, forget how concepts of how they actually infect people. Just look at the pure numbers, and this will make sense to you as well. That having more and more vaccinated people provides this shield wall against infections by this infection by this virus, right? So I hope that clears it up a little bit.
For sure. And it also highlights how, in terms of immunity and immunology, it's clearly not just a play of biology, but also a play of numbers, right? Where we do need to look at
Yes.
data, and that comes into play quite a bit. And I think that's always surprising to me because when we are learning biology in school, we're so focused on the specific aspects of it, and we don't really see the interdisciplinary connections. And I wanted to check with you about sharing a little bit about your experience with biology and learning it in Ashoka and coming to realize the interdisciplinary connections between the same.
Yeah, definitely. Should I just stop sharing and then talk about this?
Yes, for sure.
Yeah. So I started my Ashoka journey in biology in 2021, where after I finished high school, I was part of the undergraduate batch of 2024. And that's when I took some of the first biology courses at Ashoka. So just to give everyone else a little bit of context, the first semester at Ashoka is usually involved with taking foundation courses. And the second semester is where you actually take your intro courses to different subjects. So, for example, I took Intro to Biology 1 and one of the biology lab courses. I actually came into Ashoka being really passionate about animal behavior and ecology. And so, if you did read my description a little bit, you'll find that I want to go into aging biology and neurodegeneration, which are very heavy molecular and cellular biology and neuroscience concepts. So, I wasn't even prepared for that. I was ready to come into Ashoka, work in animal behavior labs, or work in ecology and get some kind of wildlife experience as well. But I was so enticed and enthralled by our classes in molecular biology and cell biology. And we have some really great professors who really know what they're talking about. And that really helped me fall in love with the more minute forms of biology in the molecular and cellular sense. And it completely turned me over. So, in the sense of interdisciplinary, I think biology itself is a huge field that people don't even understand. And forgetting the fact that it can actually intersect with so many other departments like mathematics or physics or chemistry, especially. Biology itself is just so vast. And Ashoka does a great job, I think, of actually giving us the opportunity to delve into the other departments in relation to biology as well. For example, neuroscience is connected between the biology and the psychology department. I also took a lot of biophysics courses, which enabled me to look at biology from a different point of view. Something I mean, the math I wasn't really fond of, I'll be honest, but it did give me a lot of perspective into how differently you can look at systems when you have a huge breadth of knowledge and when you understand how principles from different fields actually work. A lot of major biological discoveries have actually been done by people with a physics background, and same for chemistry background as well. So I think Ashoka, at least in my time, it did a great job at exposing me to different forms of biology and to how biology can intersect with different fields as well. I would be happy to take questions from the participants as well about any query you have of biology at Ashoka. I was also the biology rep, so I do know what I'm talking about, and I'm very used to taking student concerns as well.
I also do feel like I hoarded all of the questions about the simulator. So please, participants, feel free to unmute yourself or raise your hand and ask any of the questions. I'm sure you have plenty of them.
For people who joined late, did you get a chance to look at the simulator properly? I would be happy to go over it again if you want me to.
You may have a shy bunch. Should we just go over the simulator once more, Nihar? And then I would actually like to give a glimpse into what we've planned in the program and touch upon some of the things because they're really in connection with the interdisciplinary aspect of learning at Ashoka. And I really want to highlight that soon as well.
Yeah, definitely. Let's just take another 2, 3 minutes to look at the simulator again. I'll just pull that up. Yeah, so for people who joined late, in this webinar, I was talking about the concept of herd immunity. And this link that I found has a really great and very simple demonstration of how different immunization rates, which means that different sections of the different portions of the population are vaccinated against a specific virus, actually lead to decrease in spread and eventually a fastened killing of the virus and a removal of it from the population. For example, here we have one infected individual amongst a bunch of susceptible ones. We have a 0% immunization rate. So the only way to get immunized against the virus is through getting infected and then recovering from it. Yeah. Just from the start, we can very easily see that it really is a chain reaction that happens when a new virus comes into a largely susceptible population. and just leads to a huge amount of people very quickly getting sick before some portion of them actually recover. While this is like Isha was talking about, while this is a way that the population can acquire herd immunity, it's incredibly dangerous. And we don't want to expose people with weak immune systems or immunocompromised individuals to natural infections as much as possible. So here you saw that every participant in this population definitely became red and then recovered from the virus and became green. Now let's look at a 50% immunization rate.
I have one question
Yeah.
here at the 0% as well. I think it's also based on this assumption, right, that after a person has recovered, they won't get reinfected. Whereas in COVID,
Yes.
what we noticed was that with different waves, if you have recovered from the first wave, you can still get reinfected. So the math we are
Correct.
seeing here is actually not replicating reality, whereas herd immunity without vaccinations would take many, many more years, right? Because you need to get recovered from multiple strains of the virus as well.
Very true. That's a really good point. And one of the things that actually came up in the waves against COVID was that, especially people who were on the recovery rate between people who got vaccines versus people who didn't was huge. There was a huge gap in people who were just infected by different strains who did not get vaccinated, and they struggled a lot with their recovery. I'm sure a lot of us have unfortunately had not great experiences with COVID. I know I did. And so I won't spend a lot of time talking about that. But I will say again that vaccination is a huge and very important bioengineering technique. And the reason it's gotten so much social and political limelight is because it's been incredibly important in keeping us safe from pandemics like what happened with COVID. So let's look at what 50% immunization rate would look like. Here, half of the population is vaccinated. So you can see that the infected individual on average will have a lot slower time in spreading the infection. That's not to say that there's no infection. Again, we haven't reached the threshold for herd immunity yet, but it is a lot slower than what we were seeing for the 0% immunization rate. Honestly, even at 50%, it's a little faster than I would like. I wouldn't want this many people to be infected at all if I could help it. One of the first things I was talking about when I started discussing herd immunity in this webinar was that it is as much for you as it is for the people around you. It really is a population level policy to have, and it helps not just you, but the people around you, especially people who are immunocompromised. So please keep that in mind if you ever think about, oh, I'll just skip my vaccination dose. Okay, great. So we've been able to eradicate this virus as well. Now let's look at almost complete vaccination rates at 95. Yeah. Here you can see that the infected individual, just by chance, is having a really tough time actually interacting with any susceptible individuals at all. And they recovered, not a single infection. So this is a very simple demonstration. It just goes to show how important and potent and powerful vaccination really is, and how important vaccination campaigns are as well.
You seem to
Yes,
have a
Myra, please
hand
go ahead.
raised, Myra. Please go ahead.
Yeah, so seeing the simulation, we saw like the benefits of a larger percentage of the population being vaccinated. So, do you think it should
Correct.
be made mandatory in case of like a global healthcare emergency, like maybe a pandemic that has a very high mortality rate?
Of course, it should definitely be mandatory. Though, of course, there's a lot of social and political issue that comes with making vaccinations mandatory, and there is always a small segment of the population that doesn't want to get vaccinated.
Right.
I personally do think vaccination is mandatory, and of course, when newborns turn 6 months and I think 7 and 9 as well, there are compulsory vaccinations that people are supposed to take and give to babies as well. So vaccination itself should definitely be mandatory whenever we're in a global health emergency.
And like we've had more research into this field recently, but why do you think that still, in terms of like um, society and people in general, there's been a rise in sort of fear against vaccines and people who don't want to be vaccinated outside of just like immunosuppressed people or people who can't get it because of their religion?
Right. Great question. And this also goes to show how interdisciplinary biology is, especially in the real world, right? So I'll make 2 points to answer your question. The first, and then we'll go to your question, Reena, as well. The first point is that in the recent, I would like to say last 3, 4 years, there's been a huge increase in distrust towards science. And that has been brought globally due to a lot of different political movements going on. And due to that, as well as some erroneous science communication, there's been a lot of belief that vaccines actually cause harm to the individual in some way. There's been a lot of studies that seem to link vaccinations to things like neurodevelopmental disorders or autism, for example. And a lot of this is fabricated, a lot of it is miscommunicated, and it really goes to show that science communication is an incredibly, incredibly powerful tool that we as researchers need to use to make sure that the public is well educated, especially in times where, from the political side of things, there's a lot of mistrust in science being pushed by different governments in power. So I hope that addresses your question a bit. The second point I wanted to make was that um, a lot of the studies that seem to show this kind of harmful effect of vaccines, and when you delve into it, you'll find a huge, huge internet hole here, is that they're backed by certain corporations and certain governments. They've gotten funding from a certain group of people that would like to see that agenda being proposed forward, right? For example, recently we've seen in the United States that there was an advisory on decreasing the amount of vaccines required for children to reduce some kind of burden that their healthcare segment was having, which obviously is not something we want to do because vaccinations are incredibly important, especially for young children, right? So yeah, I hope that answers your question a little bit.
Yes, thank you.
Yeah, Reena, you had a question as well?
Oh yeah, I had a question. Is herd immunity possible for all the diseases that people face throughout the whole world?
Right. So let's look into what vaccines are, right? Vaccines are inactivated or weakened form of pathogens which help our immune system recognize the pathogen and prepare to encounter it in the wild, correct? Now, even what happened with COVID was that why were people being infected again and again? Because the strain was changing, right? There were so many different types of COVID running around that even if your immune system was prepared for one type, there would be one more type that comes and it's harder for the immune system to recognize it. That's not to say vaccinations don't have any benefit. Even if the immune system can recognize one strain of a virus, it helps it recognize the next one as well. Now, because of that, and because of how a lot of different diseases work, for example, bacterial and fungal diseases are not something that we have proper vaccinations against yet. It's something that is being developed, and I hope in the future maybe you can contribute to it as well if you're very interested. But yeah, there's a specific set of viral disorders that we can get vaccinated for, and because of that, it's not something that can help you deal with all the diseases in the world, but it is definitely a very potent tool to deal with a huge amount of viral disorders, especially. Does that make sense?
Yeah, yeah. Thank you.
Yeah, Kirti, I saw your hand raised and you put it down, and I want you to ask your question anyway. You can also type in the chat if you're having troubles with your mic, like you were telling us earlier.
Hello, am I audible?
Yes, yes.
Yes, sir. This might be a basic question, but I was wondering that we know that many viruses spread easily through contact, like touching surfaces or being near infected people. So why can't we design vaccines that spread in a similar way so they can reach more people, especially those who cannot afford on access vaccination? Or is there any ongoing research that could make such self-spreading vaccines safe and ethical in the future?
Okay, so that's an incredibly cool question. I would love to see the development of something like this. As far as I know, there is no self-spreading vaccine that is in development right now. A reason for that is because let's say you have a bottle of this liquid that's basically the vaccine itself. Spreading it to a lot of places would may not work because the vaccine contains a weak form of the pathogen, right? The form might just die and it might just crumble and it might not even last in the wild, right? A lot of the times when you see vaccines being transported, they're done so in small refrigerated boxes because it's very important for them to be kept at that temperature until it's injected into the body. right? Where the immune system can actually recognize it. And if you just put all of this liquid, for example, on different surfaces, because of things like temperature and weather, they might just disintegrate and they might just degrade over time, leading to a very ineffective spread. It might not even help you get the immunity that you want. Now, a small segue from your question, releasing a weakened form of the pathogen is something that people have been trying to do in the context of mosquitoes, where people are trying to engineer mosquitoes in a certain way that they can't carry disorders like malaria and dengue anymore and releasing them in small sections of the world. Those studies are happening. If you would like, you can reach out to me over email and I would love to share the relevant articles with you. But so far, self-spreading vaccines, not really there.
Of course, I would like to have your email for this type of discussions.
Yeah, I'm sure we will share it at the end of this webinar as well. So definitely be on the lookout for that.
Okay,
Yeah.
thank you so much.
We'll also share it with the participants in the email that we share after the session. So we'll make sure that they can get in touch with you for the same. I did want to check with the participants if we have any more questions about the simulator or anything else that you'd like to ask Nihar before I move on to discussing the program a little bit more and getting his insights for the same. All right, I'm going to get started, but please feel free to interrupt me as and when you like. Just give me one moment. And I'm hoping that this should. Is my screen visible? Yes. So I'm actually going to walk you through some of the program modules that we've come up with for the biosciences course that's happening in the summer. And the reason why I'm doing this is I actually find it incredibly fascinating that the project modules go beyond what we understand of biology and also come up with a theatrical element. There's history coming in as well. So, the first project module that you're working on is actually designing Pokemon like cards, where immune cells are characters with powers and weaknesses. And it really excited me because imagine that you have a card like Pikachu or and you're kind of trying to come up with something that this is a power that the immune cell has and this is a weakness that it has. I would like to go into the technicality of it, but honestly speaking, with my lack of background in biology, I don't think I can say much more. But if you were to ask me about Pikachu, I can tell you a lot more. That I have some expertise in. And we also have enacting a role play where you're actually putting up these disguises because it's a great point, right? Where it's our immune system that sometimes starts attacking the own body as well. So, how does it manage to actually do that? How does our immune system turn on us? Or how are viruses present in our body for years before they even get noticed as something that is actually attacking us? So, these disguises is something that you get to enact in the Great Escape. The retro from the future is the most exciting one to me because you're actually doing a creative writing project and actually letting your imagination run wild, where you're trying to imagine future transformations in immunology. And Kirti, I think your question really touched upon that, right? Where why can't we have a self-spreading vaccine, and what would that mean for the world? I actually find it really fascinating that we already have artificially engineered mosquitoes that we're trying to work on for dengue and malaria because that's going to have a huge impact if we are able to actually make that happen. I still remember how bad it gets when it's dengue season in Delhi because the amount of collected water that we see everywhere is too high. So it's really difficult to actually protect yourself against these environmental factors. So if we can just take care of it at the initial level itself, that can be a huge impact. And lastly, you're creating a museum wall of history and the breakthroughs in immunology. And I think that touches me really personally because if we don't pay homage to the big changes that have happened in the past, then we can't really imagine the future. And I think that's the thinking that's gone behind it. So, with these kind of project modules, I think you're going to be able to have a lot of fun and interact with your peers as well. I want to pass the mic to Nihar and to share a little bit about what you're excited to cover the most in the course.
I mean, like you said, Isha, the Pokemon cards, I'm looking forward to that so much. I think we're going to have a great time with that. I'm also looking forward to the creative writing project as I'm really excited to see what people can imagine maybe happening. And the most important aspect of this course for me, at least, is the Museum Wall of History, because I feel, like you said, Isha, rightly, you really need to understand the shoulders you're on when you're doing research, right? There's been a lot of great people doing a lot of great things in biology and adjacent fields that have led us to actually having the knowledge that we have right now. Even the most recent Nobel Prize was actually in immunology and given to immunologists. So if you know what that topic was, then please put that in the chat. I will not tell you definitely. But it was an immunological concept that was given the Nobel Prize, and three, I think, two or three immunologists that actually got it. So immunology is incredibly relevant in the current events, and I'm really looking forward to having building that museum wall of history with the students as well. And of course, I'm really looking forward to interacting with the students and answering any questions they might have with Ashoka. That's something I've done a lot, and I'm looking forward to meeting everybody in the course as well.
I think with your experience as the biology rep, the students are going to actually have this one advantage of getting to know more about how it is like to study biology in Ashoka. They get the insider info early on while they're high schoolers. So I think that's going to be particularly exciting. With this, I'm going to move back towards the presentation. And I know that we've been speaking about biosciences, but we're actually offering a catalog of 9 courses this summer. So, for all of the attendees, if you ever want to do one more course along with biosciences, because I know that you're all interested in biosciences for sure, we have been able to see that with the high engagement we've had. You can actually look into these. In addition, one we're going to start on May 23rd and finish on June 14th. And addition two starts on June 20th and finishes on July 12th. And the biggest advantage is that the classes are happening on weekends only. So, in case you do have your school hours ongoing, you can still do the program. We've decided to go with 2 editions because we've recognized that in India we have such varied academic schedules. So, it's important to cater to both of them. And we have a great cohort that's sizing up for the cosmic dance of your immune system. Some of the students are doing incredible work already. So there's a lot of peer learning that's going to be happening in the course as well. As you saw, we're going to be working on projects, and you're actually going to have a demo day where you're going to present your capstone project as well. And lastly, and most importantly, I want to share about the extended opportunities that are going to be offered in all of the courses. So, in the past, we've had internships, mentorships, observerships across courses. For last year in biosciences, we actually had 2 students who came into Ashoka and were able to spend some time in the cutting edge labs, speak to the PhD students and the professors, and they were able to do some of the experiments themselves. You can actually see Soha right here, who's doing the experiments herself, and she was able to meet everyone. This is Professor Sandeep Ameta. So I'm very excited for this opportunity being available for this year as well, where you can actually interact with Professor Deblina in person and come to campus if you perform really well in the course. And a second opportunity in place is that you could actually visit the Bose Institute that's based in Kolkata, because Professor Gautam Basu is the lead there, and you would be able to access some of the cutting edge labs present there as well. So those are 2 very exciting opportunities, and I would really recommend students to not only participate in the course, but to do your absolute best so that faculty has a difficult time choosing top 3 students and they have to extend it to everyone, because these are incredible opportunities to have access to at an early age. Lastly, we've gotten really great experiences out of the students, and we're hoping to pursue the same this year as well. A biggest thing that we've echoed from the past students is that doing the course actually gave them clarity as to what they want to study. And I think a major part of that is the TF interaction they have, because they're able to speak to an expert in the field who's able to give them insights as to what is it going to be like to study this at a collegiate level, what are some of the potential career paths post that, and that kind of clarity at 16 is so helpful. We also have grade 9 students who join us who are able to have that clarity much early on and get an early edge. So that's something that's in store for you as well. With this, I'm going to stop, and I would like you to scan this link. We'll also share the link and the email ID in the chat box in case you want to just access it through that. I'll open the floor up for any questions that you may have, whether they may be program related as to what is happening in the biosciences course, or whether they may be about the timings of the program or what all are the demands of it, or whether they may be about the simulator. We're going to open it up to questions, and I'm going to stop sharing my screen right about now. Thank you so much all for joining us. It's been an incredible morning filled with a lot of learning. I know that I'm going to be taking away a lot from what you've shared, Nihar. So thank you so much for taking out the time to actually guide us through what herd immunity is and also taking on questions that go beyond the same. Any questions from the attendees before we close? And if I don't see any hands raised in the next 1 minute, I'm going to assume that we have done a lot of that we've done a lot of good jobs in terms of being able to go over some of the concepts today. All right, perfect. I think we're going to give each other a pat on the back. We've done a great job in able to cover the concepts and the program details. Thank you all for joining us this fine Saturday morning. It's been great learning about herd immunity with all of you. Thank you so much, Nihar, for actually lending your expertise about biology and on studying biology at Ashoka and sharing about the program. We're incredibly grateful for your time. And thank you, Virat, for your support throughout the webinar as well. Thank you, everyone. Have a nice day. Bye bye.